You know that little brick that charges your laptop? Or have you ever wondered how a massive electric car gets all its power from a standard outlet in your garage? Well, the answer to both is this incredible, kinda hidden world of technology called power electronics. And in this explainer, we are going to pull back the curtain and show you exactly how it all works. This really is the invisible revolution that powers our modern lives.
All right, here's what we've got on tap. We're going to start with the big picture, defining what power electronics even is. Then we'll get into its secret sauce, efficiency. After that, we'll look at the actual tools of the trade, the switches, the math behind them, and finally, how engineers bring it all together.
All right, Section 1, Defining Power Electronics. Let's kick things off by getting on the same page. What is this stuff, really, and what makes it different from, say, the processor inside your computer? So here's the deal. It's all about processing energy, not information. I love this analogy. Think of your computer's CPU as the brain, like a librarian, right? It's meticulously managing all this data, the ones and zeros. Power electronics, that's the muscle. It's the power plant and the entire grid getting energy to the library. It doesn't care about the data. Its job is to do work. It's all about moving power from point A to point B in the exact right form, with as little waste as humanly possible. So how does it do this? Well, it all boils down to 4 main jobs. First up, AC to DC, using something called a rectifier. You use this every single day. That charger for your phone or your laptop, it's taking the AC power from the wall and turning it into the DC power your battery needs. Okay, so what about the other way around? That's DC to AC, and for that, we use an inverter. This is absolutely crucial for things like solar panels. They generate DC power, but your house and the grid run on AC, so the inverter makes that switch. Third, you've got DC to DC converters. These just change one DC voltage to another, like stepping down the 400-volt battery in an EV to the 12 volts needed to run the radio. And last, we've got AC to AC controllers. These are a bit more specialized, used for things like changing the speed of huge industrial motors.
Okay, Section 2. This is where we get to the real secret sauce of power electronics, the core idea that makes everything else possible. It's a relentless, obsessive focus on efficiency. How do you manage huge amounts of power without just burning it all up as heat?
So, back in the day, if you wanted to lower a voltage, you basically just used a resistor to burn off the extra energy as heat. It worked, but it was incredibly wasteful. Imagine trying to control a fire hose by just putting your hand over the nozzle partway. You're fighting the flow, you're wasting all that pressure. Power electronics had a much smarter idea. Instead of a valve that's halfway open, it uses a switch, and that switch is either 100% on or 100% off. There is no in-between.
And this is the light bulb moment, the core concept. An ideal switch uses zero power. How is that even possible? Well, think back to your basic physics, right? Power equals voltage times current. When the switch is off, yeah, you've got voltage across it, but there's zero current flowing. So anything times 0 is 0 watts. And when it's on, you've got tons of current flowing through, but now there's 0 voltage across the switch itself. Again, 0 times anything is 0. In either state, no power is lost. It's genius.
Okay, wait a minute. You might be thinking, if I can only turn things fully on or fully off, how in the world do I get, say, half the voltage, right? How do you get anything other than all or nothing? It's a great question.
And the answer is this absolutely brilliant trick called pulse width modulation, or PWM for short. Instead of leaving the switch on or off, you just flick it on and off really fast. We're talking thousands, even millions of times a second. By controlling exactly how long it stays on during each tiny little cycle, we call that the duty ratio, you can control the average voltage. You want 50% voltage? Keep it on for 50% of the time. You want 20%? Keep it on for 20% of the time. It's that elegant. And this high-speed switching is why your phone charger is so tiny today compared to one from 20 years ago.
Of course, that leaves you with a really choppy signal, right? On, off, on, off. So what do? You just run it through a simple low-pass filter, usually just an inductor and a capacitor. The filter is like a bouncer at a club. It's designed to block all that high-frequency noise from the switching and only let the smooth, average DC value get through. And boom! Just like that, using a switch and a simple filter, you've created a super efficient, stable power supply.
All right, Section 3. So we've been talking a lot about this perfect, ideal switch. But as you know, in the real world, nothing's perfect. So now, let's get practical and look at the actual parts engineers get to play with to build these things. Basically, all these real-world switches fall into 3 big families. And the main difference between them is just how much control an engineer actually has over them.
uncontrollable, semi-controllable, and fully controllable. First up, the diode. This is the simplest of them all. It's basically a one-way street for electricity. You have zero control over it. It just turns on or off based on what the rest of the circuit is doing. They're the workhorses you find in the most basic power supplies, but they're not perfect. At high speeds, they can get a little leaky, letting current flow the wrong way for a split second, which wastes energy and creates heat.
Then you have the big guns. Thyristors, also called SCRs. These are for when you need to control a ton of power. Think giant industrial motors, high voltage power lines, that kind of thing. They're what we call semi-controllable. You can flip them on with a little electronic nudge to their gate terminal. But, and this is the catch, you can't turn them off. They stay latched on until the main current flowing through the circuit naturally drops to zero.
And that brings us to the most flexible tools in the toolbox, the fully controllable transistors. With these, you can turn them on and off whenever you want. The king of the hill right now is the MOSFET. It's controlled by voltage, which makes it super easy to use with modern microcontrollers, and it's ridiculously fast. Then you've got the IGBT, which is this really cool hybrid. It kind of combines the easy control of a MOSFET with the high power capability of an older type of transistor, the BJT. The BJT itself isn't used as much anymore, mostly because it's slower and a bit more clunky to control.
And this table really puts it all into perspective. It shows you the classic engineering trade-off. There's no one-size-fits-all solution here. Need blazing speed for a tiny phone charger? You're grabbing a MOSFET. Need to handle the insane power of an electric train? The thyristor's your guy. Need something right in the middle for, say, an electric car's motor controller? The IGBT is probably your best bet. It's all about picking the right tool for the job.
Okay, section 4. So, with all this crazy fast switching going on, the electrical signals, the waveforms, they look pretty messy. They're definitely not the nice clean sine waves you see in a textbook. So, to make sense of it all, engineers need some pretty slick mathematical tools.
The big one is called the Fourier series. It's this amazing piece of math that lets you take any messy repeating signal, like the output from our switch, and break it down into a bunch of simple, clean sine waves. The analogy of a musical chord is perfect. The Fourier series is what tells you every single individual note being played in that complex sound. This is absolutely critical for calculating power and, more importantly, for designing the filters to get rid of all the noise you don't want.
Now, if you want to get even fancier, especially for designing the control systems, there's a technique called state space averaging. Your circuit is constantly flipping between two states, right? Switch on, switch off. This tool mathematically combines the equations for both of those states to create one single averaged model that describes how the circuit behaves over time. This is how you design the brains of the power supply to make sure its output voltage stays rock solid no matter what.
All right, last section. Let's bring it all home. How do engineers actually take all these concepts, the switches, the topologies, the math, and use them to build something that actually works?
Well, the first thing you have to understand is that you don't just start soldering things together. Not with these circuits. They're complex, and they're often dealing with high, dangerous levels of power. So step one is always simulation. Engineers use powerful software like PSpice to build a virtual version of the circuit right on a computer. They can test everything, look at every single voltage and current, and iron out all the kinks long before a single physical part is ever ordered. It's absolutely essential.
So there you have it. You've got the basic toolkit. You know about the switches, the control methods, the analysis tools, but that really just leads to the big question, the one that defines all of engineering. Which tools do you use for which job? An EV charger that has to handle thousands of watts safely is a completely different beast than a tiny laptop charger that needs to be as small as possible. And that's where the real art and science of design truly begins.
And really, that was our goal for this whole explainer, to give you those fundamental building blocks. You now have a solid grasp of the switches, the core concepts, and the models engineers use to understand this invisible world of power conversion that runs, well, pretty much everything around you.
Hey, if you made it this far and you found this useful, it would mean the world to us if you hit that subscribe button and gave this video a like. But more than anything, we want this to be a conversation. So let us know in the comments, what do you want to learn about next? A deep dive into MOSFETs versus IGBTs, a hands-on tutorial on the Fourier series, or maybe something completely different? Let us know what you think. We'd love to hear from you. Thanks for watching.